our job is to find out that how these chi plus and chi minus are acting as the basis set for these states. So let's start with this one, and let me write for example, I want to find out the matrix representation of S square. If I want to write S in matrix form, then how I will be able to write this one? So the matrix representation of S square. What is S square? It is the square of this spin. It is an operator, just like we were having over here we were having an operator L square and LZ. In the same sense, we will have operators S square and SZ here. Square operator, and then the orientation operator, one component of this, which we call the Z component. So let's write this one, that when S square operates on chi plus, what it will give you? You remember that what was S from this terminology? S square is S into S plus 1 h bar square. So this will be S into S plus 1 h bar square. And this is equal to S is our spin half case only. So half into half plus 1. Half plus 1 will become 3 by 2. 3 by 2 into 1 by 2. 3 by 4. This is 3 by 4 h bar square. Clear? From the angular momentum terminology, and in the previous lecture we have written from that analogy that S square will be equal to this is L square was L into L plus 1 h bar square. If this S square operates on chi minus, what it will be? Again it will be S into S plus 1 h bar square. And okay, one thing I forgot, here I will have to write chi plus. Here will be S square, so the S square value is this one. Here will be chi plus and here will be chi minus. So this will be equal to, and here we will have to write chi plus. This will also be equal to 3 by 4 h bar square chi minus. Because S is the same, it is the M which changes. Plus half and minus half. So if it operates on chi minus as well, we will get 3 by 4 h bar square chi minus. Now, as we said that all our spin matrices will be 2 cross 2 matrices, and I want to know the matrix representation or the matrix form of S square. So I consider that let me write that our S operator or S square operator is a matrix which is C, D, E, F. This is 2 by 2 matrix. So I will have to find out the values of C, D, E, and F. Then I will be able to find out this. So there are 4 unknowns here, C, D, E, and F. Let's start from the first one, this one. And here I know that when S square operates on chi plus, I am having 3 over h bar square chi plus. So this implies that for S square I will now write my matrix which is C, D, E, F, and for chi plus I will write 1, 0 is the eigenstate 1, 0, and here this is 3 over 4 h bar square and 1, 0. When you do multiplying, what will you get? C into 1. So it will be C. Then D plus D into 0. So 0. So C plus 0. It will only be C. While here only E will remain and F will become 0. So you are having C and E. CE is equal to what? 3 by 4 h bar square 1, 0. When you apply this means when you multiply it here, so it will be 3 by 4 h bar square and 0 here. So you can compare this. C is equal to 3 h bar square by 4 while E is equal to 0. So you wrote that from here C comes out to be 3 over 4 h bar square while E comes out to be 0. And similarly, when you write the second term, and the second term is that when S square operates on chi minus, it gives again 3 by 4 h bar square and chi minus. Right? This implies that write C, D, E, F, and for chi minus 0, 1, and this is equal to 3 over 4 h bar square 0, 1. Now this implies that now C is 0, D is 1. So 0 plus D. You are having D remaining here and you will have F remaining here is equal to 3 by 4 h bar square and 0, 1. And this will give you that D is equal to 0 and E is equal to 3 over 4 h bar square. Yes? Yes, this will be F. So 3 by 4 h bar square and 0. So write the values of S square then. S square is S square is C, D, E, F. Now 3 by 4 h bar square is here and 3 by 4 h bar square is here. So if I write this, then the value of C is 3 by 4 h bar square, D is 0, then E is 0, and F is 3 by 4 h bar square. And this is equal to 3 over 4 h bar square. If I take this common, then this is 1, 0, 0, 1. Only on the diagonal I am having non-zero numbers. So I can write that the matrix representation or the operator S square is equal to 3 over 4 h bar square 1, 0, 0, 1. Clear? And this is the matrix representation or the matrix form of S square. Similarly, we want to find out the matrix form, of, we want to find out it after S square, we want to find out it for SZ. So the SZ matrix form we want to find out, then how it will be looking, and similarly SX and SY for spin-half particles. Means how this will look like. The very first one that we will have to do here is to first find an equation form of this thing. First we will find the equation form, and then we will convert the equation into matrix form. You know about this fact that when SZ operates on an eigenstate, and this is S and M, this is an eigenstate and this is in a kit notation. So we are having S and then the angular momentum and then the orientation of this angular momentum in a given direction. What it will be? It will be equal MH bar and SM. You know this fact from here. When LC was operating, it was MH bar. So with the same analogy, I am writing MH bar and with the eigenstate. So this means that when SZ operates on chi plus, then this is equal. Chi plus is an eigenstate, so it's a spin-half state. When SZ operates on chi plus, what value it will give? It will give MH bar. What is the value? Means H bar is here, but what is the value of M associated with chi plus? Half H bar. So M is half, then H bar, and then what will happen to the state, to the chi plus? SZ is operating on chi plus. So the state will remain chi plus, only the value will be half. When SZ operates on chi minus, then the value will become minus, while the state will be the same. State is the same, only the value will be changed, because M is possessing two values for spin-half, plus half and minus half. So we will have to do this correction. Right? When SZ operates on chi plus, it will give you an eigenvalue half H bar, while the state will come in as it is. When SZ operates on chi minus, it will give you a value minus half, while the state will remain as chi minus. And then we will have to find out the values for SX and means this one, SX and SY. And you know, when we were finding the values of LX and LY, we were converting them into L plus minus operators. So here we will convert them into S plus minus operators. So we start with this one, that we want to find these values, and let's see. When SZ operates on chi plus, so for SZ I write C, D, E, F, means these are the 4 unknowns. Chi plus, I know that this is 1, 0, then half H bar and 1, 0. So what this will give me? This will give me C and E, and it will be equal to half H bar, because 1, 0 and 0. And this implies that C is equal to half H bar while E is equal to 0. Clear? So simple. Similarly, when C, D, E, F, when this applies on chi minus is 0, 1. It is minus half H bar and chi minus. So 0 and 1. So here D and F will remain. DF rather will become 0, and 0 and minus half H bar. So this gives you D is equal to 0 and F equal minus half H bar. So this implies that for SZ, the matrix representation, if I take H bar over 2 is common, then C is equal to 1 and D is equal to 0. So 1 and 0. While E is equal to 0, so here it is 0, and F is equal to minus 1. So this is the matrix representation of SZ. Got it? The matrix representation of SZ. Now look at the matrix representation of S square. As it is a square, we are having H bar square. As it is one component of it, we are having H bar. Right? Here, this is the eigenvalue, and this is the state of it. 1, 0, 0, 1. Here is 1, 0, 0, minus 1. Here is a difference. And this is how we can put the matrix representation or matrix form of SZ. And now we will calculate the matrix form of Sx and Sy for Spin-1. Now we will start with the matrix representation. Matrix representation of S plus minus. It means Sx and Sy. SZ we have already determined. Now you remember from that analogy of the L plus minus that this is Lx plus minus ILy. Similarly, we will have S plus minus, and this will be equal to Sx plus minus Isy. We will use these terminologies, but here things are a little different, and the reason for that is that we were having many states available here with L plus minus, but with S plus minus we are having only 2 states available, and the 2 states are spin up and spin down. Is these 2 we call the ladder operators, the raising and lowering operators. So the ladder operators here, Either it will rise a state or it will lower the state. But unlike the orbital angular momentum, in spin angular momentum, we are having two states only, and the two states are, this one I call chi plus and this one I call is chi minus. Only two states are there for spin half particle, and this one is having eigenvalue plus half h bar, and this one is having eigenvalue minus half h bar. There are no more states here. So when I will operate S plus on chi plus, as it is a raising operator, it will raise the state chi plus, but there is no further state available. So it means this thing will be equal to 0. And when S minus will operate on chi minus, then there is no more state available below as well. So this will also be equal to 0. While for the S plus minus, I am writing a compact relation. When S plus minus operates on a state Sm, then this will be equal to h bar S into S plus 1 minus M into M plus minus 1, and this is inside a square root. And then the state S, while M will become M plus minus 1. You can write this in bracketed form as well, but we know that this is the spin and this is the orientation of that spin.